Mechanics is the name of the game. We play with objects, subjecting them to motion under the application of forces. The rules of the game, known as laws of motion, have been derived from extensive studies on the behavior of bodies in nature, from falling apples to the motion of planets in the sky. The laws enable us to analyze the motion of bodies under the application of forces and to estimate the forces for the design of systems to create the desired effects. The action and effect aspects of mechanics applies to deformable bodies, flow of fluids, continuum, and often extended to socio-economic systems. But we will confine ourselves to the mechanics of rigid bodies and point objects, that's particles. It is not the same laws which apply to the entire expanse of size and velocities of bodies. We shall limit ourselves to classical mechanics. Material objects larger than subatomic particles with speed less than, say, 10% the speed of light obey the laws of classical mechanics. Of course, we shall take the state of rest as a special case of motion being zero. Mechanics is at the core of all science and engineering because of its far-reaching applications in high-rise buildings, flyovers and bridges, in the design of electrical machines, in biomechanics and rehabilitation, and in vehicles for transportation on land and overhead, and perhaps in everything around us. All this makes mechanics a fascinating subject indeed. Let's have an insight into some of the basic concepts to clarify them. In order to visualize the external forces acting on a body, it is necessary to start with a free body diagram. A free body diagram is that which isolates the body from its surrounding and shows all the external actions upon it. Let's look at two cylinders placed in a V groove. For the upper cylinder, the free body diagram consists of weight, normal reactions from the groove and from the lower cylinder. For the free body of the lower cylinder, the weight, reactions from the groove and from the upper cylinder. And now, when the two are taken together, the action and reaction between the two do not appear. Only the weights and reactions do. Let's look at a common example, the free body diagram of a block sliding up an incline under the action of weights placed in the pan, includes the frictional force F, normal reaction N, string tension T, and of course the weight W of the block itself. A question: what is the value of the frictional force F? Is it mu times N? What about the frictional force F for a rolling cylinder rolling down the incline? It is best to begin with the postulate that the limiting shear stress tau is proportional to the normal pressure P between the two surfaces. Mu is the coefficient of static friction. If the shear stress has the same direction over the entire area of contact, then integration of this results in the well-known equation F max equals mu times n. This is true only for impending slip. Two bodies with surface contact may have no slip, impending slip, or slip relative to each other. For no slip, the frictional force may be anywhere between 0 and a value just short of mu times n. For relative slip, F assumes a value mu d times n, where mu d is the coefficient of dynamic friction, 10 to 20% less than the coefficient of static friction. Now look at a case such as a thrust bearing. You can't apply F equals mu n, but you can determine the frictional moment by considering tau equals mu p at a radius r and then integrating to find out the total moment m. A cylinder placed on an incline may go down in one of the three ways: without slip, with impending slip, or it may slip while rolling. For rolling without slip, the value of the frictional force is again between 0 and the maximum value F max, whereas for impending slip, F max equals mu n, and for slip, F is equal to mu d times n. The direction of the frictional force F is not obvious. Does it always oppose motion? Would you like to draw the free body diagram of a vehicle for a hind wheels drive and for a four-wheel drive? Let's try. In a normal two-wheel drive, the front wheels merely roll. The power of the engine is used to turn the hind wheels, which push the road backwards. The road merely obliges and pushes the car forward. The frictional force on the wheels is in the forward direction. This is only a fraction P times the maximum possible friction, that is mu times mg. In a four-wheel drive, all the four wheels are powered and the vehicle can get the maximum possible forward thrust, mu times the weight of the vehicle. Once we have a clear idea of the forces and moments acting on a body, the laws of motion are used to determine its motion. It was Newton who discovered the laws of motion for the center of mass of a body. His second law, often called the law, states that the rate of change of momentum of a body is directly proportional to the force impressed upon it. The momentum equals m times vc, the velocity of its center of mass. Hence, the impressed force equals mass times acceleration of the center of mass of the body. The force referred to is the vector sum of all the external forces, and the acceleration is only that of its center of mass c, regardless of whether the force sigma f acts through c or not. For a point mass, that is a particle, the resultant force and the acceleration are collinear. Newton's laws do not cover the rotational motion of a body. It was Euler who postulated an additional law for rotation by considering the mass distribution of the body, that the rate of change of moment of momentum of a body equals the moment impressed upon it about a point fixed in the frame of reference. The simple form mz equals izz times alpha is valid only for a rigid body undergoing fixed axis rotation. Now, how would you proceed to determine the state of motion of the robot arm at this instant? Where would you locate the frame of reference? robot arm is acted upon by forces F1, F2, etc. and moments M1, M2 and so on from the adjoining links as shown in the free body diagram. The Newton's law is applicable only for an inertial frame of reference. We cannot choose the origin anywhere on a moving body. A frame of reference is said to be inertial if it is either at rest or in motion at a constant velocity. A frame which either rotates or accelerates is a non-inertial frame. A frame fixed at the center of the solar system appears to be the best inertial frame for us, assuming negligible force acting on it from outside. A frame at the center of the sun is the next best. A frame at the center of the earth is the best approximation for an inertial frame for long-range missiles and earth satellites. However, a frame located at the surface of the earth is a good enough frame even though it rotates a complete revolution in 24 hours. Then any frame fixed respect to the earth or moving at a constant velocity is good enough, as the acceleration would be the same, referred to any inertial frame, as the addition of a constant velocity makes no difference to it. Let's also look at the concept of equilibrium. By definition, it requires that every material point of a body should be at rest in an inertial frame. From the laws of motion, it follows that sigma f equals 0 and sigma m equals 0 for the whole body. But then, these are only necessary conditions of equilibrium and certainly not the sufficient conditions to ensure equilibrium, because even when sigma f equals 0 and sigma m equals 0, a body such as a spinning top is not in equilibrium. Different material points have different velocities and accelerations. Now let's look at a vehicle of mass m negotiating a turn of radius r at a velocity v. Is it going to skid or is it going to overturn under the influence of centrifugal force? Let's pause to think what centrifugal force is. Is it a real force for an inertial observer? First of all, let's understand that the vehicle turns into a curve by virtue of the radially inward force called centripetal force. This is provided by the friction between the wheels and the ground. Beyond a critical speed for a given radius r and frictional coefficient mu, the vehicle may skid radially outwards while following a tangential path. During turning, the reaction at the outer wheels is more than that at the inner wheels. At a certain speed, the overturning moment may exceed the stabilizing moment and it overturns radially outwards. No wonder someone said, be soft on the curves. Are you surprised that the radially outward overturning of a car has been explained without invoking centrifugal force? Well, there is no such thing as a centrifugal force for an inertial observer. Let's look at the motion of a particle from an inertial reference and from a non-inertial reference. The inertial observer notices an acceleration AC. The non-inertial frame has a linear velocity v0, acceleration a0, rotational velocity omega, acceleration alpha. The non-inertial observer notices an acceleration am of the same particle. What then should he do to apply the Newton's law? The inertial observer may apply the Newton's law F is equals m times AC, whereas the inertial acceleration comprises acceleration of the moving frame, a tangential component, a radial component, and a Coriolis component, with respect to the moving frame. Non-inertial observer may apply the Newton's law, alright, by clubbing the minus m times acceleration just named with the external force F. These additional force terms are called inertia forces. In particular, minus m times omega cross r, which reduces to mv square upon r radially outwards, is called the centrifugal force. That explains why a non-inertial observer sitting in a car notices loose things going outwards as he himself feels being pushed outwards. The inertial observer, on the other hand, can neither see nor feel the inertia forces. The same thing is explained by invoking the D'Alembert's principle, where the Newton's law is written in a frame translating with respect to an inertial frame at the center of mass of the system. For a particle traveling at a constant speed v along a circle of radius r, the inertia force equals mv square upon r in a radially outward direction. That is the centrifugal force for a rotating observer. Of course, there are many alternative formulations of the Newton's and Euler's laws and special cases called principles. The impulse momentum principle states that the impulse of a force on a system equals the change in its momentum. And in the absence of external forces on the system, the total final momentum equals the total initial momentum. The work energy principle states that the net work done by the external forces on a rigid body equals the change in its kinetic energy, which reduces to the conservation of mechanical energy principle in a conservative force field. And then there is the conservation of moment of momentum principle in the absence of any external moment acting on a body or a system. Now, why these principles and which one do we apply under what conditions? Is there a preference for one over the others in some situations? If so, which one would you apply for the impact of two bodies, and which one to explain the gyroscopic principle? The principles are the first integrals in time and space for the same laws. That's why they make the things easier. When the force is an explicit function of time and we wish to determine the velocity, we prefer to start with the impulse momentum principle. In the absence of an external force on a system, we employ the conservation of momentum principle. If the force is an explicit function of displacement and the objective is to determine the speed as a function of position, we employ the work energy principle. If, however, the force varies with velocity, we invoke the basic laws. In an impact, there is no external force or moment on the system. It is best to apply the conservation of momentum principle. If, however, we wish to find the average force during impact, we estimate the time and then apply the impulse momentum principle on either body. The gyro couple is perhaps better conceived by applying the Euler's equation itself. I am sure you can conceive many more problems and try solving them yourself by applying the laws and principles of mechanics. This is what mechanics is all about, helping us solve problems and design newer systems. You can sum up the thoughts that triggered your mind. Perhaps you can review the trigger shots again and conclude it for yourself.
Kumar.